Section 3.5, Rational Functions. Rational function. Think ratio, think fraction. That's what we have here. N for numerator, D for denominator. We can have a rational function as long as D of x, the denominator, is not 0. A rational function is made up of a polynomial in the numerator and a polynomial in the denominator. Let's look at an example and a non-example. So far, it looks good. But if you put 0 down here, no, this is not a rational function. Again, the numerator looks fine. The denominator isn't 0. It's a polynomial function, so yes, this is an example of a rational function. Just think fractions. All right, some of the things we're interested in with regard to rational functions would be the domain. You have to be careful when you divide, okay, in a fraction, divide, because you don't want to divide by 0. So we have to be concerned about any variables that are in the denominator and what numbers that you place in for that variable, say x, would create a 0, because that's not a rational function. So the domain of a rational function includes all real numbers except x values that would make the denominator equal to 0. So if you're asked to find the domain of a rational function, here's an example. Think the reciprocal function. Well, if x is ever 0, it can be anything but 0, but if it is 0, you're dividing by 0, so 0 cannot be part of the domain. Our approach to finding the restrictions on the domain would be to look at the denominator, disregard the numerator, it has no effect on anything, and state that x cannot equal 0, or whatever's down here, whatever expression is down here, whatever polynomial function is in the denominator, just set it to does not equal 0. So in this case, x can be any value except for 0. So for the domain, we exclude 0 from all real numbers using interval notation. And just to include a graph to get an idea of what we're dealing with, you might remember the reciprocal graph has a branch in quadrant 1 and in quadrant 3. As you sweep across from left to right, notice that all x values are present on this graph except for the value of x equals 0. So that graphical representation supports what we just found. All right, let's look at the domain of another function. I'll call it f again. If we're asked to find the domain of this rational function, disregard the numerator. It has no effect on anything. The domain question deals only with the denominator. We never want the denominator to equal 0. So let's factor and find the values of x that we want to avoid. Factors nicely. We don't want x minus 3 to be 0, so that means that when you add a 3 to the other side, x cannot be 3. These are your restrictions. We don't want the factor x plus 2 to equal 0, so that would mean that x could not be negative 2. So taking all this information and reporting the domain, we only have 2 numbers we need to exclude. Well, thinking about the order of these numbers as they fall on the number line, we're going to go from negative infinity up to negative 2, restrict it from being in our domain. Then we're going to continue from negative 2 up to the other restriction of 3. And then from 3 to infinity, all those numbers are good. If you wanted to look at a graph to verify that, if you were to type this equation into your calculator, you're actually going to have a vertical asymptote at -2 and +3. You're going to have a vertical asymptote at these x values. Whew. And the graph looks like this on your calculator. That branch stays above the x-axis. This part of the graph right here is like a downward opening parabola. Kind of has that basic shape, although there's no symmetry. And then on the other side of x equals 3, the graph does something like this. So visually, if you were to look at this graph, you could support that this domain is correct, because as you sweep across from left to right, the only x values that are excluded would be at x equals -2 and x equals 3. Alright, so we're interested in the domain of a rational function. We're also interested in if the rational function has any vertical and horizontal asymptotes. Okay, sometimes a rational function will have a vertical asymptote, sometimes not. Sometimes a rational function will have a horizontal asymptote, sometimes not. In these previous examples right here, the reciprocal function actually had a vertical asymptote at x equals 0, and it has a horizontal asymptote at y equals 0. So x equals 0 is a vertical asymptote, and the horizontal asymptote is y equals 0. Over here in this graph, x equals -2 was a vertical asymptote, as was x equals 3 a vertical asymptote. Now the horizontal asymptote does exist here. The further you got to the left or the further you go out to the right, this graph is leveling off. We don't care about what's happening in here. It's just extreme left, extreme right. Okay, we also have a horizontal asymptote at y equals 0. So both these graphs had vertical and horizontal asymptote. This one had 2 vertical asymptotes compared to that one right there. Again, like I said, all rational functions behave a little bit differently, so you might not have a vertical or a horizontal asymptote. Alright, let's look at some definitions, and then on the back of our worksheet we'll put these definitions into practice. So vertical and horizontal asymptotes of a rational function. So here's your rational function. Don't let all that scare you. What you might want to take away from this is that in the numerator, the highest exponent, or the degree, of the leading term is n. And in this notation, they let m be the highest exponent in the denominator. So it says, let f be this rational function where n and d have the numerator and denominator have no common factors. And it goes on to tell us that the graph of f has vertical asymptotes at the zeros of the denominator. We've already done that, as long as there's no common factors with the numerator. However, the graph of f has holes at the zeros of both the numerator and denominator. What that means is if you have a common factor with the numerator and denominator, the zero of that factor doesn't give you a vertical asymptote, it gives you a hole. We'll see that on the back of this worksheet when we do some examples. Okay? So that was a description of vertical asymptotes. Now, going on to horizontal asymptotes, the graph of f has at most, of a rational function, has at most one horizontal asymptote determined by comparing the degrees of the numerator and denominator. Remember, in the numerator, n represented the highest exponent, and in the denominator, m represented the highest exponent in the denominator. And so we're going to compare them. It says if n is less than m, then the graph of f has line y equals 0, or the x-axis, as a horizontal asymptote. We have 2 examples that we can refer back to. Okay, if you go back up here to these examples, okay, if you look at this function right here, coming down here, n equals, well, that's the highest degree in the numerator. Well, I can fill in an x to the 0, because x to the 0 is 1. Now that's kind of weird, but x to the 0 is 1. The understood exponent here is 1. So in the numerator, n would be 0, and m, the highest degree in the denominator, would be 1. So in this case, n is less than m, and what they're saying down below is that if n is less than m, that we should have a horizontal asymptote, and we did. So look at this example over here. Again, you can fill in an x to the 0. So in that case, n equals 0. In the denominator, m is going to be 2, the highest degree. We'll compare these two numbers, which means n is less than m. But it says down below that if n is less than m, that y equals 0 is a horizontal asymptote, and it was, just visually from what we saw. Okay, well, that's not the only way that those degrees would compare. What if they're equal? Then it goes on to say that we have a horizontal asymptote, and it's going to be the coefficient, the leading coefficient of the numerator and the leading coefficient of the denominator. We'll see that on the back when we do some examples. And then it says if n is greater than m, if your exponent on top is bigger than your highest exponent at the bottom, then we don't have a horizontal asymptote. And that's going to actually produce a slant asymptote, but that's not of concern for us in these notes. Okay, on the back, let's find all asymptotes. That means vertical and horizontal. In that language, it means all asymptotes, vertical and horizontal. And let's also find out if we have any holes. All right, holes mean that we have a common factor in the numerator and the denominator. We're going to find out if we have any holes of these rational functions, and if so, at what x values do those holes occur. What I'd like to do is I'd like to tackle the whole question first. Looking at all of these examples on the back, I want to tackle that one question. And then we'll come back and look at vertical and horizontal asymptotes for each of these questions. So holes. All right, the numerator is completely factored, as is the denominator. So if they're completely factored and nothing cancels, done. No holes. Because we have no common factors. Let's write that down now so that later when we look back at these notes, we'll remember why we said no holes. Look at example B. The numerator is factored. The denominator I can factor into x minus 1 and x plus 1, but neither one of those factors will cancel with anything in the numerator. So as in the first example, we have no holes because we have no common factors. Let's look at example C. The numerator is factored. The denominator probably is going to factor, but when I do factor it into linear factors, I'm not going to be able to cancel with the numerator. No holes. No common factors. Example D. I can't cancel anything. No holes. No common factors. Example E. Well, it looks like I'm going to have to do some factoring here to determine if I have any common factors with the numerator and the denominator. X and x, factors of negative 2 that add to positive 1 would be plus 2 and minus 1. Denominator factored, x and x, looks like minus 3 and plus 2. Notice the common factor of x plus 2. If we have a common factor, then we have a hole. And the hole will occur at the x value of the 0. So if you were to set this common factor equals 0, you're going to get a hole at the x value of negative 2. Now, if you have a common factor and it's just numeric, no variable, then there's not a hole. It's only when you have a common factor that has a variable in it. Look at example F. Factoring the numerator, sum and difference of like terms, because it's a difference of two squares. Denominator, you can take out an x. So it's not a binomial times a binomial, it's just x taken out multiplied by x plus 5. There is a common factor of x plus 5. The 0 of that common factor is negative 5, so we do have a hole occurring on the graph, if we looked at it, at x equals negative 5. All right, we have more work to do with the vertical asymptotes and horizontal asymptotes, and we'll do that in the next video.